Hello everyone, welcome back to the Simscope. In this video, I will present the design and modeling and the performance analysis of a interconnected electrical power system developed using the MATLAB Simulink and the Simscape Electrical. Uh, the system represents a realistic multi-voltage power network consisting of a generation, transmission and distribution stage operating at 132 kV, 33 kV and 11 kV. The project title was Design and Operation of an Electrical Power System. So the project aim is to design and operate the interconnected electrical power network, which has two generator, four transformer, five transmission line and two load of residential and industrial load. We have to maintain effectively effective operation and power factor while keeping the 132 kV buses within plus or minus 2% and other buses under plus or minus 5% voltage. So this is the voltage that we have to keep. The main objective of the model is to evaluate the voltage, stability, power flow, system losses, efficiency and impact of power factor corrections under different loading condition. Overall system overview. The Simulink model represents um, this single line diagram of a network. The system includes of two synchronous generator of 11 kV and 6.6 kV and four different transformer uh, which will step up 11 kV to 132 kV and 6.6 kV to 132 kV. Then it will transmit through the transmission line. At the distribution side, 132 kV voltage is stepped down to 33 kV and it fits to the industrial load. Further, for the residential load, there is a one transformer which will step down from 33 to 11 kV and the residential load of 20 megawatt will be served. With these two load centers, in the Simulink model, we have transformer 1 and transformer 2 which will generate the power. Then each generator has a transformer and transformer 1 here, this is a transformer number 4. Then it will generate the power and transmit through the transmission line, this transmission line. And at the load side we have our first load, the industrial load of 10 kilowatt here and the second load here. So in the distribution side we have transformer number 2, transformer number 3 which will step down the voltage. The power is generated on the left hand side of the model. It is step up to 132 kV, then it is transmitted through the long transmission lines. It is step down to supply at the load at 33 and 11 kV. This is the overall overview of the Simulink model. Now, moving into the specifically the generator modeling. Um, as per the load, we have calculated the generator's rating and impedance. Then, after calculating the generator's source voltage, generators kVA, MVA, and its uh, inductance and resistance. Then we are going to put the values in the generator sections. We are using a three-phase source, and for this block the generator 1 is supposed to generate 11.3 kVA. I mean the 11 kVA. However, uh, considering that this power is going to be transmitted through the long transmission line, there is a power losses when we reach at the load side. So due to the resistance in the transmission line and the uh, transformers losses and the transmission line losses, we have taken the um, point 0.03 0.3 voltage higher in the generator 1 to compensate the losses, and the frequency is 50%. The internal uh, resistance and inductance values are given here to um, make the generator more realistic. Then generator 2 is this one. It should generate 6.6 kV, and both the generators are modeled in a realistic internal impedance using the per unit values with x over r ratio of 10 and subtransient reactance of 8% and 10 8% here and 10% respectively. This ensures that the generator behaves like a real machine under a load rather than uh, an ideal voltage source. Next is the transformer calculation. Transformer parameters are calculated with the x by r ratio of 15 and impedance of 6%. A lot of information are here. You can go through it. I'm not going to talk the details, but we require an equivalent voltage. We know the voltage. We have to find the impedance, z equivalent, r equivalent, x equivalent. Then finally find r1, x1, l1, r2, x1, l2 at hp and lp site. Okay, this is the transformer 1, transformer 2, and transformer 2, transformer 3, and transformer 4 calculated in the. So in the model, this is transformer 1, so it should stepping up the 11 kV to 132 kV. The transformer 1's winding, internal winding is star, and secondary winding, sorry, the primary winding is connected in star and secondary winding is connected in star, and the core type is single phase. The winding parameters that we have calculated is inserted here. The nominal power is 30 MVA for the transformer 1. It is stepping up from 11 kV to 132 kV. Then the primary R and L values, or the resistance and inductive values, are punched in here. Similarly, transformer 2 here with these parameters. Transformer 3, sorry, this is a transformer 2, this is a transformer 4. This is transformer 3. This will step down the voltage from primary side is 132 and 33 at the, and we have a transformer 4 or transformer 3 here, which also steps down the voltage from 33 to 11 kV. Okay, In total, four transformers are used in the network to interconnect the different voltage levels. Uh, each transformer has rated impedance of 6%, as I said, and the X by R ratio of 12. Then each transformer, for the model accuracy, the leakage impedance is shared between the low voltage and high voltage side. 40% on the low voltage side and 60% on the high voltage side. This configuration ensures acceptable voltage regulation within plus or minus 2% for at 132 kV and plus or minus 5% at low voltage level. That's the transformer modeling. Let's move to the transmission line modeling. For the transmission line modeling, you have to consider uh, you have to first calculate the current traveling through current flowing in the each transmission line. For example, the transmission current flowing in the 40-kilometer line is 328.24 amps, and based on that we have to calculate the cable sizing. From the datasheet, we selected two different types of cable: 795 kcml ACSR for 132 kV transmission line and 1800 kcml aluminum conductor for 33 kV distribution line. From the datasheet from the manufacturer, you will get resistance, inductive reactance, and inductive capacitance. Based on that, you have to calculate reactance and inductance in per each transmission line. Then you can plug this in as a R and L block. For example, in case of a 100-kilometer line, we are not using the pi ready-made pi section block in this model, because we cannot uh, we want to put the calculated values for the R and L values, and transmission line can be represented by the R and L values or RL series RL branch. In the 100-kilometer, we have calculated 3.2 ohm in R and 0.055 inductance. And to make the transmission line with the distance of more than 80 is considered as uh, medium, or 80 to something is more than 80 is medium and high transmission line, and less than 80-kilometer is a short transmission line. So short transmission line can be easily represented in simply represent in RL load. However, for the long transmission line like 100 kilometers, then you need to model this in the pi section. So to make the model in the pi section, you have to use the capacitance bank or shunt capacitance in each side of the RLC branch, series RLC branch. So this is a long transmission line. You have a pi section and you have two capacitance and one RL load. This is a short transmission line for with these values of 50 kilometers. Then this two transmission lines joins together, and it is further transmitted through the very long transmission line of 200 kilometers, which is represented by this transmission model. Then you reach at the distribution site. The distribution transformer steps down the voltage, and for the industrial load your transmission line is 20 kilometer, and for residential load your transmission line is 40 kilometers. There are in this model total of there are 5 transmission lines with actual physical length of 20, 40, 50, 100 and 200 kilometers. The maximum or the longest length is 200 kilometers and the shortest is 20 kilometer. And each line is modeled using the resistance, inductance and capacitance parameter derived from the manufacturer data for ACSR conductors. This allows the simulation of a capture voltage drop. You can also find the reactance, reactive power flowing and um, active power flowing through it. What we found is the longer the transmission line, more losses because of the more reactance, and it contributes significantly to the voltage drop. That means longer the transmission line, more voltage drop, more power loss, and to compensate that we have to generate more power in the from the generator. Now moving into the load uh, modeling, two major load centers are connected to the network. Firstly, the residential load is of 20 megawatt at 11 kV, and reactive power is 20 megawatt here. So nominal voltage should be 10 kilowatt kV or 11 kV. You can put this as 11 kV, and this residential load is running at a power factor of 0.9. In case of a industrial load is 10 kVA and it is running at the power factor of 0.85. The industrial load uh, we later we reduced the power factor to 0.6 and study the impact of a poor power factor. These loads are modeled in the constant power loads, allowing us to study the system's performance under varying demand conditions. Now, the overall systems have RMS value to calculate the RMS current and RMS voltage, line current and line voltage, and active and reactive power. And you can also find each RMS values and the map in the scope. For example, I have already simulated or run the simulation. So the generator 1 is generating, it should generate 11 kV, more than 11 kV, it should generate 11.3 kV. So it's generating 11.27 kV, and the voltage from the generator is step up with the transformer 1 to 132 kV. So transformer 1 has stepped up to 135.4 kV. Then it is transmitted to 100 kilometer transmission line. Similarly, from the bottom, 6.6 generator is generating 6.6 kV voltage, and it is stepped up by the transformer number 4 to 132 kV. So it is, when simulated, we get 134.6 kV, and it is transmitted through 550 kilometer line. They are connected in parallel, and now it combines together into one long transmission line of 200 kilometer, and it is transmitted through that. We have initially around 134.7. Now when you get at the end of the transmission, a 200 kilometer transmission line, you can see that the voltage has dropped to 132.8. There is a little voltage drop here. Now the transformer number 2 will reduce the voltage or step down the voltage from 132 to 33 kV. Therefore, after stepping down, we are getting 33.16 kV, and it is feeding the 100 kilometer, I mean 100 megawatt, 10 megawatt industrial load. To feed the residential loads usually have low power, therefore it should be further reduced to 11 kV using the step down transformer, and from 33 kV, where is okay, here it is reduced to 11.27 kV. Okay, to evaluate the system's performance under the different operating conditions, load variation studies were conducted at the both load buses. We have the load was stepped up from 25% to 125% at the step of 25, right? The load were step up from 25% to 125 and of their rated value. Okay, and the simulation result shows that active and reactive power increases proportionally with uh, the load, confirming the correct per unit scaling. The bus voltage remained within plus or minus 5% for 33 kV and 11 kV buses, and within 2% for 132 kV across all the loading level. Next, we have calculated the power losses and voltage drop in the transmission line. Transmission line losses were calculated using the three-phase loss equation, and the highest loss was observed in the 33 kVA line. So transmission line of 33 kVA has the highest losses. Which one is that? Line 1 to 3. This one, because it has a highest due to higher current flowing through it. The 200 kilometer line, being the longest, has a highest voltage drop of 3.5 kilovolt, and we found that the total network line loss was approximately 1.04 and voltage drop is 7.6 kV. Then we calculated the overall network efficiency, which came around 78%. We calculated the voltage regulation. The efficiency level is reasonable for this efficiency. Overall network efficiency is reasonable for the multi-voltage systems with long transmission distance and multiple transformers. Now the power factor correction. Uh, when the when the industrial load power factor was reduced to 0.6 lagging, the reactive power demand increased significantly, leading to higher current and increased losses. To address this, a shunt capacitor was installed, and the required reactive power compensation was calculated to approximately 7.63 MVAr, or capacitance of 22.4 microfarad. After compensation, the power factor improved from 0.85 to 0.9. In the Simulink model, we have this capacitor bank connected to the load side. Now we have also done the simulation in the Simulink Power World. You can please check the link for the simulation. I'm going to upload all the files from including Simulink file, project report, and Power World simulation file for your you can download through the links that is given in the video description, and you can even check my bio for the link. We have compared the Simulink versus Power World comparison. The steady state version of the same network was modeled in the Power World, and it is mainly studied where this Power World will give you more detailed information about the losses. Then um, mm, it is it will explain you more of the flow load flow. Next, we have compared the Simulink versus Power World, and the result shows that the voltage gradually declines from generator to load side. The voltage gradually decreases. The reactive power demand was highest at the load buses, particularly in the industrial load, emphasizing the importance of reactive power management. Then power factor correction significantly improved voltage stability and reduced the reactive power. That was a short result discussion. To conclude, the project was successfully demonstrating the design and operation of a realistic interconnected electrical power system. The system maintained voltage stability within the design limit. We have achieved acceptable efficiency and showed strong agreement between the dynamic and steady state simulation. Proper transformer sizing, realistic transmission line modeling, and uh, reactive power compensations were critical for to achieve this reliable system performance. Mm, this model shows how real-world power system balance voltage and power flow, losses, and stability across a multiple voltage level. Thank you. If you learn something, please support me by giving the like, comments. Please give me the feedback, and please subscribe in my YouTube channel. As I said earlier, you can check my um, video descriptions in YouTube and go through my bio links. I have a lot of project electrical engineering related projects uploaded, and you can easily download the files and project informations from the links given. Please check out. Thank you and see you in the next video.